Welcome to Sintonía Secreta, your Secret Sintony. We are May Garcia, Carlos Mateu, and who's talking, Sergi Faber. And we do a Spanish-speaking podcast about economy, geopolitics, science, and even more fringe things. Today we have the pleasure to have with us the theoretical physicist, mathematician, and author Sabine Hossenfelder. And this is our first program in English. We are going to ask her about her book, Lost in Math: How Beauty Leads Physics Astray. Sabine Hossenfelder has a bachelor's degree in mathematics and a PhD in physics. She has written more than 60 research articles, mostly dedicated to quantum gravity and physics beyond the Standard Model. When she talks about the stagnation of physics at Sintonía Secreta, we listen very carefully. We like to learn from people who have an informed and interesting opinion about any branch of human knowledge. And we think that an interview with Sabine would make a great Christmas gift. In Hossenfelder's own words, nothing is moving in the foundations of physics. One experiment after the other is returning null results. Nothing. Zero. Nada. Nichts. No new particles, no new dimensions, no new symmetries. As she says,
nature is beautiful. Nature is also cruel. And what about the laws of nature? Most physicists today think that the fundamental laws of nature are beautiful and simple. But the natural laws that they have discovered so far are not as beautiful and as simple as they could be. And so, when they develop new theories, they want those to be simpler and more beautiful than the theories that they know already. In the past 40 years, criteria for beauty and simplicity have become mathematical requirements, and they have worked badly. They led physicists to predict new symmetries, which were not found. They predicted unified forces, which were not found. They predicted new particles, which were not found. So what do physicists mean when they say a theory is beautiful? And if criteria from beauty work so badly, why do they continue to use them anyway? Read my book to find out.
and that's exactly what we did and recommend anyone interested in this field to do. Buy the book and read it to understand why Hossenfelder does not think crisis describes the current situation well enough, and stagnation describes it better. Lost in Math begins with her frustration that despite 40 years of failure, researchers in the foundations of physics do not change their methods. She concludes that the problems in her discipline have the same origin as other recent crises in different areas of science. Groupthink, peer pressure, and professional hubris. The book finishes with a call to action and a proposal for change. Without further ado, we leave you with the interview.
We'll talk about your book. I asked Ariel, the Spanish publisher, and they told me that it will be available hopefully by June next year.
Okay, so you know more than I do.
Well, they answered 2 days ago actually. I asked them right when you told me. Right, you work as a theoretical physicist.
Yes, I'm a theoretical physicist at the Frankfurt Institute for Advanced Study.
And you work on what's called the foundation of physics?
Yes, I make this my catch-all phrase. So I work a little bit on dark matter and modified gravity. I work a little bit on quantum foundations. I used to do high-energy particle physics. I do a little bit of general relativity, and so it's quite a mixed bag.
Okay, and I've been following you since last summer, and then I watched I have read something more about your ideas in your own blog, Back Reaction, and I saw that you have wrote a book that's called Lost in Math. How is it? Why did you decide to write such a book?
Oh, there are many reasons. The probably most obvious reason is that my research is stringing along on temporary contracts and has been doing so for a while. And I've been using my writing for some while as a safety backup, in case I run out of money, I have a second leg to stand on. So, of course, I could have written a book about a more cheerful topic. I've been told that positive messages sell better than negative ones, and I guess I failed on that account. So the reason that I chose to stick with the more negative message is that I'm worried about what's going on. There are a lot of people who have gotten stuck on methodologies that clearly don't work, that have not been working demonstrably for decades. Mm-hmm. And this reliance on argument from beauty, if you try it once, it's okay. You can treat it as a kind of hypothesis, right? So you believe that the laws of nature are beautiful in this particular way, and there's no harm in trying that. You go and test it, and if it doesn't work, you move on. And exactly this last step, this we move on, try something else, never happened. And I think it should have happened in the 90s at latest. They tried this immediately starting after the completion of the Standard Model that was in the 1970s. They had these ideas of grad unification, and then string theory came along. There were the first candidates for dark matter, and they started commissioning experiments. There were the dark matter searches. There were also searches for supersymmetry at LAP, the Large Electron Positron Collider at CERN. So that's actually, they used the same tunnel that is now used by the Large Hadron Collider. And they didn't find anything. And so what happened then was that rather than saying, well, that didn't work, let's try something else, people just modified the theories, tweaked them a little bit, and tried the same thing over and over again. And now that the Large Hadron Collider has not found those particles either, not in the first run, not in the second run that was completed, they're lobbying to build the next larger collider. And I'm like, well, where will it stop?
Exactly.
Yeah, so, and I had the feeling that the public has been very misled about the promises of these experiments, is being misled. I was just looking at an advertising video for the next larger collider, what's it called? Something with the Future Circular Collider. That's the plan by CERN for the next larger collider. And in this video, they make a lot of statements that are just not correct. Like you cannot use this collider to probe the origin of the universe. That's complete nonsense. And if this happens in like a popular science video that runs on TV, that's all fine by me, because we know these things have to sell, and I have a lot of understanding for that, trust me. Okay. But if it comes from a scientific institution, that's not okay.
Yeah, and why do you think they are making this kind of advertisements and not realizing that all the experiments so far haven't found what the theorists predicted?
Well, I think they totally realize that. It's hard not to notice, but I think there are multiple different reasons that play together there. One is definitely wishful thinking. They're like, we have not seen it so far, maybe we will see it the next round, and you cannot rule it out. Okay, so I'm certainly not saying that I know they will not see anything. I would never say something like this because nobody knows. So in a world where we had infinite resources, I would say, sure, go and build this next larger thing. If it takes $10 billion, who cares? But that's not the world that we live in. And we have to be really careful with where to put our money. So this wishful thinking is certainly part of the story. It adds to this that there are a lot of people in these communities, right? If you count the high energy particle physicists of the world, that's several thousand people. And now you have this large community of people who are all convinced that they're doing the right thing because they think that there must be more. The standard model cannot be it. The hierarchy problem is supposedly a huge problem and the standard model should be natural, but it is not. So there must be more to find. They want the forces to be unified. And they think that these are perfectly fine reasons. And that's what they've been taught, that's what they've learned in their education, and that's what they constantly hear from each other. You know, I've been to these conferences and it's like they're all saying the same thing. And of course, they are very certain that that's the right thing to do. I mean, these are not stupid people, right? I mean, they have brains, but it's really hard to sit in a group of 1,000 people who all believe in something and say, nah, actually, you know, I don't buy it. It just doesn't happen, right? And so that's certainly part of the story. And then there's also that they are stuck on this, right? You have people who work in high energy particle physics. What are they supposed to do if there will be no more particle collider?
Okay.
Right? I mean, they need this to continue, and they have a lot of good reasons to advertise their stuff. They need money, you know, they need the next larger thing to keep producing papers. And so I think basically that's where it comes from. But still, I think it's not okay that a scientific institution supports what is, you know, claims that are abundantly untrue.
Uh-huh. Because you said that the finding of the Higgs boson was the only one that actually worked with the large.
Yes, and that prediction goes back to the 1960s. So definitely not a new thing. And this prediction of the Higgs boson was not an argument based on beauty. It was a mathematically very rigorous argument, you know, I would say good methodology. And now all these other predictions for the supersymmetric particles and for the weakly interacting massive particles and the extra dimensions and the tiny black holes and all that kind of stuff, they were all based on arguments from beauty. And that's what my book is about, right? So it explains these different types of beauty and how they enter the development of these theories and why I don't think that any of this is science. So I'm not terribly surprised that this did not work out. It's just not good scientific method. And yes, so I want to say this once again, I cannot predict what will happen in the next run. Maybe they find something. That might totally be the case. No one knows. But either way, we already know that all these predictions were wrong. They are ruled out. If any of that would have been correct, we should have seen it by now. Indeed, if you look at what people said before the LHC turned on, they said, we will see it immediately. If supersymmetry is there, it will be right in our face. It should be a big signal. And then, well, they turn it on and it didn't see it. And everyone was like, yeah, you know, there's no reason to be concerned. We will see it eventually, you know. And then it was not in the first run. It was like, yeah, it will be in the second run. And of course, now they're like, yeah, you know, we're still collecting data. Maybe it will show up eventually. But by the way, let's talk about building the next larger thing.
Yes, the subtitle of your book is How Beauty Leads Physics Astray. And what's the definition of beauty for in your field of research? What does it mean, beauty?
That's the interesting thing is that in the foundations of physics, people have developed very narrowly defined notions of beauty that I've summarized in the book. So the first one is simplicity. And I always stress I'm talking about absolute simplicity, not relative simplicity. you can use relative simplicity as a good comparative measure. If you have different theories, you pick the one that explains the same data in a simpler way. That we do that all the time. That's how science works. So that's not what I'm talking about. I'm talking about absolute simplicity in the sense that you want laws of nature that are absolute, period. So a good example for this is that we have this thing that's called the Standard Model, which combines 3 different forces. That's the electromagnetic force and the 2 nuclear forces, the strong and the weak nuclear force. And they kind of awkwardly sit next to each other. And it would be so much simpler if they were then under certain circumstances can split up and look like it's 3 different forces. So that's called symmetry breaking. And the reason people like it is that it's simpler. It's axiomatically simpler if you start with 1 force than if you start with 3 different ones. So that's an example. Another thing, maybe string theory. So you have this idea, everything is made of strings. That's definitely a simple idea. Devil's in the detail. So there's simplicity. Then there is this notion of naturalness, which is particularly influential in high energy physics. And that's the argument that all of these predictions for the Large Hadron Collider were built on. So naturalness is a property of a theory in which the parameters without units, so the ones that are only numbers, should be close by 1. Not much larger than 1, not much smaller than 1, but kind of just right. And that's presently not the case for the Standard Model. So there are some dimensionless numbers that are awkwardly small, 10 to the minus 15, and physicists don't like it. That's what's called the hierarchy problem. And now what you can do to remove this problem is you can conjecture that there are new particles that come with a new symmetry. Supersymmetry is a good example for that. And that will render this small number natural. Okay, so now you have an explanation for why it's small. And that's why a lot of physicists thought that this must be the case, because it would be so much prettier. You no longer have to conjecture that this number is 10 to the minus 15, but the symmetry actually tells you that it should be the case. So I should add, you don't necessarily need supersymmetry to do that. You can do something else. But the bottom line is always that you need to have some kind of new physics that appears close by the Higgs boson. And that's what the LHC has tested. So now if you find new physics at higher energies, it will no longer fulfill this criteria. Okay, so naturalness is still being used, by the way. People are now trying to push it up to higher energy scales. So now suddenly, I was just looking at slides from a talk where someone now suddenly claims, oh, naturalness, by the way, predicts that we should see new physics at the next larger collider. Guess what? Yeah. So that's the miraculously adaptive argument from naturalness. Yeah, and then there's the third criterion of naturalness, that is the vaguest one, which I've summarized as elegance, which is that physicists want a theory to hold some surprising insights. Some people call it unexpected connections. It's this aha moment where the theory tells you something new that you didn't know in advance, something that you didn't put in. General relativity is a good example for that. General relativity is a very simple theory. It's based on a few geometric principles, but it has a lot of very surprising consequences. It gives rise to black holes, gravitational lenses, gravitational waves, light bending on the sun, redshift and the gravitational field, all that kind of thing that you didn't expect. The theory develops its own will and pushes these conclusions on you. And that's what physicists think of as elegant. And so these are these 3 criteria, simplicity, naturalness, and elegance, that physicists think are beautiful in a theory.
Okay, but you say that the reality is not like that. Always. Not
Well,
always. Doesn't conform to this criteria.
The reason that physicists use these criteria is that they have been useful in the past, or at least they think they have been useful in the past. So definitely symmetries have been dramatically useful in the development of the standard model. And in hindsight, also in the development of special and general relativity, though this might not have been all that clear to Einstein. Naturalness is also a good criterion in the sense that the standard model is technically natural, except for the mass of the Higgs boson. Okay, so there is something odd about the mass of the Higgs boson, and it's not so surprisingly, you know, everyone knows what the reason is. The Higgs is the only fundamental scalar particle, so it's a different particle, it has different properties, and one of those properties is this issue with the mass. And physicists don't like it. They don't like that this particle is somehow different, and they want it to be as it was before. Basically, they want everything to be technically natural. So these criteria are experience-based, and that's all well and fine. But the problem is that if you're looking for a theory that may be based on entirely different mathematical principles than the one that the current theories are based on, then these criteria of beauty derived from theories of the past may just no longer be useful. And so there's the risk, if you continue to apply them nevertheless, you'll get stuck on them.
Okay. And in your opinion, what should be the right path to go along?
You know, I hate it if people ask me this. You know, it's not that I'm a genius or something and can tell you do this and that will be the solution. So yeah, the main message of my book is that I want people to think for themselves. Just because there are some thousand people telling you that naturalness is a good thing to look at, it doesn't mean it's correct. You know, look at the data. The data tells you naturalness does not work. It has, in fact, we've known this for a long time because the cosmological constant is not natural. It just isn't. So why are we even still talking about this? And you know, even if you were trying to ignore the cosmological constant, which actually a lot of particle physicists do because they think that has something to do with gravity and that's not our business. Now you have the data in your face, right? I mean, the LHC did not find all these things that were predicted based on naturalness. So maybe can we please finally stop talking about it and throw out this criterion from naturalness? So really, I wish people would think about it themselves. Of course, I have my own ideas of what would be better things to do that are not surprisingly the things that I work on myself. Okay. Right? Huh? Oh yes. So I told you in the beginning, I'm working on modified gravity dark matter things. So I think that's a good problem because we know that something is there. At least we know it's there, right? We have a lot of data. And personally, I think that we have enough data already to figure out what it is. We're just not analyzing it the right way. Okay. So that's one thing. Then another thing that it briefly comes up in the book is that I think we're not paying enough attention to the foundations of quantum mechanics. There are some odd things going on there with the measurement that have been largely forgotten, and people are not thinking about it all that much. So this is also something that I think more attention should be paid to. There are also various problems with the formulation of quantum field theory, where there are just issues that are not fully understood. This also briefly comes up in the book, right? So I'm not going into any detail about this. No, of course. But like the non-perturbative formulation of quantum field theory is a problem. There are some other issues with these theories where we haven't fully understood how we're even supposed to handle them. So this is also good, solid research, I would say. What else? Oh, yes, there's quantum gravity, of course. So a lot of people seem to think that I'm a string theory hater. So I'm not, everyone who hears this, I'm not a string theory hater. So string theory is based on a very good motivation, which is that we have this issue that the standard model doesn't want to work together with gravity, Einstein's general relativity. They're incompatible. And to resolve this problem, we need a theory of quantum gravity. And string theory is one approach to that. It does a pretty good job. So it's a well-motivated approach. Now, there are a few other approaches, and personally, I think what is missing here is a contact to experiment, because eventually, no matter how well-funded your mathematical arguments are, you need to go and test it. And now there's the issue that people who've been working on quantum gravity, and this is a problem which has been known since the 1930s, by the way, so there's no means new thing. They've totally ignored the possibility that you may be able to actually test this, because, and I find it hard to understand where this came from, but they tend to think that it's not possible to test it. So now let me ask you this. If you're a scientist, you're working on a theory that you actually do not believe is possible to test, why would you work on it?
Yes, it seems pointless.
Yeah, so I find this really hard to comprehend what's going on there. But in any case, so I think it's just wrong. I mean, you can test it. Maybe it will be difficult to test it in the regimes where gravity is strong. That would be things that happen in the center of black holes or in the early universe. So it's not totally impossible, but it's definitely hard. We're not going to visit the center of a black hole anytime soon. But in the weak gravity regime, I think it might be doable. Maybe in the next, 20 years. I don't know. I'm not going to bet on it, but I don't think it's impossible, and this is just something that people don't work on. It's totally crazy. There are not even predictions for what such an experiment would measure based on any of these approaches.
Yeah, it's surprising. It's surprising. And if you could explain to people like me who are not physicists, well, why is there a need or a wish for a unified theory?
You mean unified theory of the three interactions, or with gravity?
With Einstein's theory and quantum mechanics theory. What?
Well, because with gravity, we need it because we know that the theories that we presently have are just mathematically inconsistent. There are cases that occur in nature, for example, the inside of a black hole or the early universe, which we cannot describe with the theories that we presently have. It's not working. And we know that nature somehow manages to do it. So there gotta be a way to describe it, but we don't know how. It's because, we have the standard model of particle physics, and all these particles have quantum properties. But the gravitational field of those particles, according to Einstein, does not have quantum properties. And that just doesn't fit together. It's not consistent. And so quantum gravity is the theory that's supposed to solve it. And as I emphasize in the book, I think we would be well advised to focus on problems that are mathematically well defined. So lack of beauty is not a mathematical inconsistency. It's definitely something that disturbs people. But I'm like, so what? Nature is under no obligation to please you.
It's an example of the wishful thinking you told earlier, no?
Yes, but the search for quantum gravity is not of that type, because we do not only want quantum gravity because that would be pretty, but because we actually need it.
Mm-hmm. Okay. And how's been the reception so far of your book among your colleagues?
Basically none. So among the people who actually work in the field, I think they don't want to talk to me. They're just hoping if they ignore me for long enough, it will go away and they can continue the same way that they've always done. As I told you in the beginning, they're already making plans for the next larger collider where they will continue exactly the same stories, presumably. And who knows, they might get away with it. Who am I? Yeah.
Sorry, you are the one saying that the emperor is naked.
Yes, but it's been said before, right? I mean, maybe not in high energy particle physics, but when it comes to string theory, certainly. We had these books by Peter Woit and Lee Smolin 12 years ago, and look what's come out of it. Nothing. It has basically not made any impact. They've just continued to do what they've always done. And yeah, so I also got a lot of feedback from people in other areas of physics and in other disciplines of science, largely to say thank you. And I always thought so, and I'm glad someone said it. And also, you know, in brackets, and I'm glad it wasn't me. And a lot of people also report that they see very similar problems in their own fields. This is actually so Lee Smolin told me exactly the same thing, that after he published his book, he got a lot of email from people in other fields who said we have exactly the same problems, that you get research bubbles, you know, where communities of people counting up to 1,000 or maybe sometimes even more become self-supportive, basically because they tell each other that it's a good thing to do. And if you have a lot of people working on a field, it looks like it's important. So funding goes in it, and then people go where money goes, and money goes where people goes, and it becomes this cycle where it's basically impossible to stop a research agenda.
Yes, you also said or write about an index. If I didn't understand it correctly, please correct me. That measures the number, the production of a physicist or a scientist, and the number of references how colleagues refer to these papers, and you say it's a little nonsense that index really.
Well, no, I didn't say that. I mean,
sorry.
so that's something that is very commonly done, that if you're applying for a job, if you're applying for funding for your research and so on, you have to demonstrate that you're producing papers, the more papers, the better, basically, and that your papers are regarded important by your other colleagues, and the way that you document is that they are getting cited. And there are easy ways to measure this. That's the benefit of it. It's really simple to show up with a number for that. And a lot of attention is being paid to these numbers, you know, not only by scientists, but by funding agencies and by people in the university administration. They need a quick and easy way to assess what's going on in their departments. And those are the numbers that they use. And those numbers are, of course, not entirely nonsensical, by no means. You know, it certainly makes sense that you publish your research. And yes, it tells you something about the productivity of people. And yes, the number of citations tells you something about the impact of your work on the field. That's certainly true. But the problem is, once you start rewarding people to excel according to these measures in particular, it becomes a game where the scientific quality and also the power of a theory to describe nature becomes of secondary relevance. What is important then is instead that you please your colleagues, because if they like what you do, they will cite your paper, and it will get easier to get it published, and you will get good reviews, so you have it easier to attract funding. And that's a problem which has been known for a long time. Most scientists are aware of it, but they also have no way to really fix it, not individually. So this is known. There's a large literature about these type of problems known as a collective action problem. It's like everyone individually on their own, if they would say, I don't want to play in the system anymore, would put themselves at a strong disadvantage and probably be kicked out. Like if I would go and say, I don't want to publish papers anymore because I would rather sit in my office 4 or 5 years and think deep thoughts. And I also don't care if anyone cites my papers. I would be out of a job, and that would be the end of the story. And of course, everyone knows that, so they don't do it. And we could all together make a difference and change this, but it's hard to coordinate this action.
Well, you tried, no? You published.
Still trying.
I saw that you, with 2 other people, did a website with another measure.
Oh, yes, right, exactly. Yes, you're very well informed. Yeah, so this is something that I'm still working on. So this is a little side project that has been funded by the Financial Questions Institute. Mm-hmm. And so I'm working on this with 2 other people, as you said, Tom Price and Tobias Smith-Stiller. Mm-hmm. And what we want to do is that we want to offer scientists a simple way to use other measures for research activity that go beyond these simple measures that everyone uses, the number of paper and the number of citations, which personally I think if you only take the raw data, basically are entirely meaningless. If I told you my number of citations, what would this tell you? Nothing. At the very least, you would need to know what's this number compared to the number of other people who work on similar things at my stage of, what's it called, scientific age, academic age, or what have you. That would be somewhat more meaningful, and then you can go into the finer details. And now the thing is that there's a whole field of research dedicated to this. It's called bibliometric analysis. So that's basically all the information that you can squeeze out of the publication record, which is publicly available online. So the data is there. But now the issue is, if you want to have any more complicated numbers, like let's take as an example what I just said, this normalization to people in the field, this comparison, that's just something that the individual scientists cannot easily do. They could do it all on their own by writing some kind of code, but then they don't have the time to do it, and also not sufficient interest in actually doing it. And there are 1 or 2 websites who offer this commercially, or presumably they do, because I haven't signed up for it because I don't have the money, and probably so don't have most other scientists. So that's not helping the community. So what we basically want to do on this website is that we want to offer other measures for scientists so they can evaluate them quickly and easily. And there have been literally hundreds of measures been proposed in the literature, not by us, but by other people. That you may have heard of this thing that's called the H index, named after Hirsch, the H index. Yes, and there are there are a lot of other indices, like there's the G8 index and the R index and the M index and the and the A index, and so on and so forth. And one can debate this back and forth, which one is the better one, and why use this one instead of that one. But really, we would be helped if people could just use whatever they think is the right measure, because that would prevent this streamlining that everyone goes and tries to do the same thing. And so this is what we're hoping to do with this website. But of course, the problem is that I don't, I don't have a lot of funding for it, and so I'm not sure right now where it will go. So we have a little funding to go for a few months, and then we'll see.
Well, I hope it has a lot of traction and people uses it. And then,
one thing that is funny.
Then you have an argument to keep asking for funding.
But who? Right? So that's the issue. The thing is that I basically have no track record. That's what the Europeans call it. You must know this, right? The European Research Council calls it a track record. You need to have a track record, and I have no track record in bibliometric analysis, basically zero. And that makes it very, very hard for me to get any funding on that. But if you looked at the website, you probably have seen that we offer these keyword clouds that you can make from your... So right now, this only works for people who have papers on the archive, but we're hoping that sometime in the future, we can extend this to other databases. But the funny thing is that I was recently looking at websites of some people who I was, I was looking up their papers and trying to find out what else that I'd done, and they actually had this cloud on their website. I mean, that was so exciting. I was like, people actually use it.
Yeah, why not? It can be a wonderful tool.
Yeah, that's so exactly why we did it. So that makes me very happy.
Okay, so what will be your next project, or what are will you continue to work in your area, or are you thinking of changing your area of investigation?
Well, I'm constantly thinking about this. I presently working on a research. Actually has nothing to do with what my book is about. It's something about fluid analogs for gravity. So this is a completely different thing that I've been working on for some years. And I have another research project, as I already mentioned, about modified gravity that I'll probably be working on for some longer. And I have a long-standing interest in the foundations of quantum mechanics, but this has stalled because I could not find the time or the funding to actually work on it. So now just a few weeks ago, I heard the good news that I got a little research grant. So I'm now I'm hiring a postdoc. And so there will hopefully be some paper coming out of this at some point. And I may be writing another book. I've said it.
That would be great.
Yeah, but it will take a few years, so it's nothing that will happen quickly.
Well, you will continue to publish posts on your blog regularly.
Yeah, I'm trying to do this. It's a good practice, and I've learned a lot from the blog. From the feedback that I get from people, from the references that they send me, from the corrections that I get. So I try to keep this up, but sometimes it's really hard. Sometimes I just don't find the time, and most of the time, if I write something for the blog, I actually do it on the weekend. I just don't. I try not to post things on a weekend because the traffic is miserable. So.
Well, but it's a great thing for, at least for people like me, that wants to understand how this world works, but are not physicists myself. I am not. But really, I remember that I read a post that you made right after Hawkins passed away, and I get the impression that you are not afraid to call things like they are. To speak your mind, because you didn't sugarcoat your opinions, and it's great. Because you told that the last theory of Stephen Hawking was not that great, for example, no?
Yes, that's.
And it seems a little controversial, but.
Yeah, that was the paper with Thomas Hertog, right? Yes, that was a little oversold. Yeah. I guess I'm glad I got this across clearly. Yeah, but no, what you're pointing out is actually it's a bigger issue that a lot of science journalism, which you see these days, is cheerleading for science. Basically, it's entirely uncritical, and that's partly, I think, that's political. It also, as I said earlier, positive messages sell better. Everyone knows that. But certainly part of the problem is also that the people who write about it, most of the science journalists, are just not competent to judge it, right? So if you show this, let's take this paper as an example. This paper from Hertog and Hawking, to your random science journalists, they have no idea what's even in the paper, right? And I don't blame them for that, because it's pretty incomprehensible math. And so I kind of feel that I have to say it because someone has to.
No, so your blog does a really good job about this, because you say what it is from your point of view. That's an authorized vision.
I'm glad to hear that you find it useful.
So please keep writing, keep writing your blog. What do you think about people that tries to do other theories or tries to produce other theories? Have you any opinion on David Toej and Chiara Marletto constructor theory? Is it any useful? Is it any use for you? If you don't,
I never looked at it. I have nothing to say about it. You can't know everything, you know. There's only so much time in the day.
Yeah, no, because that seems another point of view that maybe unifies.
Yeah, I should look at this. You know, it's there's so many things that I should look at.
Too many things. I know. Okay, so I hope that your book has a great reception in the Spanish-speaking countries. I'm sure it will be published also in South America, hopefully. And maybe people will start to realize that there should be something done about the lack of findings in all this in this field, and start looking for what you say, for quantum gravity and dark matter.
Yes, the thing is that, of course, I cannot promise that we will find something. It might just be that we're pretty much at the end. Maybe we're just too stupid to find the final answers. But certainly that we're using such bad arguments does not help. I'm thinking we would do better if we could at least get across this and focus on some mathematically sound arguments and not get stuck on these beauty tales.
Okay, because what is dark matter for you?
Oh, I don't know. I mean, what I've been focusing on with a student here at the Institute, Tobias Missler, that's the same guy who has been helping with the website, is that neither dark matter nor modified gravity is the right answer, but that the right answer is actually a combination of the two. So this is why I'm saying, I think if you were to attempt a model independent analysis of the data, it would scream right into your face that you actually need both, and that this is parametrically the simplest explanation that we should look at. So the way that you can realize this is, for example, by using a kind of dark matter particle that can, under certain circumstances, exert an additional force. So it's this additional force that actually modifies gravity. So you have it both together. You have, on the one side, you have this particle dark matter nature. On the other hand, you do have a modification of gravity. So it's really both together. Then, of course, there's the question, how would you test that, right? So how could you tell that that's the right answer? And this is something that we're currently looking at. But of course, that's my... That's my shtick. Other people have other ideas, and so I hope that we will see an answer to this in my lifetime.
Well, I hope so. I also hope so. And let's play a little game. If you had all the funding in the world, what kind of testing or what kind of experimentation would you try right now?
Oh Jesus, that's a terrible question. Yeah, okay, I'll give it a try. So the first thing that I would do, though, if I had all the funding in the world, I really, really think we need to fix these problems with the organization of scientific research. I really think that scientists all over the board should have an education in how decision-making in groups works and does not work. They should know about social reinforcement, about cognitive biases, about all the many things that can go wrong if you evaluate and share information in large communities. And that's pretty simple. I think this knowledge already exists. People have been working on this, doing these studies in sociology and decision making for the past 2 decades or something. So the information is there. It's not where it needs to be. It's not with the active researchers. And, I think it's pretty trivial to actually get it there. It's a communication problem. We need something like a website with some educational material. So if I had the money, that's the first thing that I would do. Okay, so now about the research itself, I basically already told you, right? So where I think that if you were to attempt a model-independent analysis of the data, you could find out if you are looking at a situation where you have a two-phase fluid that exerts an additional force. It's just that no one is doing this analysis because it's really complicated. And this is a good area where you could use machine learning. But again, it's hard, you have to work on it. You need, well, one thing is you need to have the data, but most of this data should be possible to get. You also need the computing facilities, which cost money, and you need the personnel so that people actually work on it. Of course, you cannot truly do a model independent analysis. You always need some kind of model, but you can do it more independently than you do it now. Then there's the other thing that I was already talking about, the foundations of quantum mechanics, where I think that there are some avenues that have just not been taken. There are some tests that were never made that I just think should be done. And again, there is lacking is both the theory. So this is something where I hope this little grant that I get will help to develop theory a little bit better. But there's also just the experiments are missing. And so these are not highly expensive experiments. We're not talking about billions, but it's still, you need some equipment, and it will come to, I don't know, maybe 1 or 2 million. It's not a huge amount of money, but you don't just find it on the street.
It's doable. It's perfectly doable. If there is
it's totally doable. It would have been doable 10 years ago, maybe even 20, but no one does it. Right. Yeah. Instead, we're investing billions of dollars into particle colliders that find nothing. And then there's the thing with the quantum gravity in the weak field limit that I was talking about. So there are actually some people who are working on it, but I'm not. I don't know right now how far they are along with the experiment. So it's a fairly long time project, and I'm not really up to date on how it's going. I certainly hope that sooner or later they will figure out how to do it. And on that account, there's the theory is kind of behind. So there needs to be some theory development done that I think should be done. So maybe we could actually use this if we get the data to tell apart some different theories. But if we don't have the predictions from the theory, we're not going to do it. So yeah, I think these are the things that I would put my money on if I had any money.
Okay. So you are positive in the idea that maybe one day we'll have all it figured out, how this reality works.
My personal opinion on this, it goes from totally pessimistic to super optimistic in a matter of days. Some days I'm just like, we'll just not get there. We're just too stupid. We don't get over this hurdle that we need to learn how to coordinate our collective information processing. We may be individually smart, but collectively we're dumb, we're beginners. And you don't only see this in science, of course, you also see it online. I think the social media, this whole fake news issue, the witch hunts on Twitter and so on, is all the same problem. We do not intuitively understand how we make decisions in large groups and what effects our actions can have. And scientists are no better at this. And sometimes I just think we'll never get over this. That's the end of human evolution. That's it.
Okay. Yeah, but
and then on other days, I think we can totally solve this because we know how to do it. And you only have to find, I don't know, the silver key to the wooden door. You know how it goes. Yeah. So.
Well, it's a very human thing. That the bottleneck is that the information flow and distribution among a large group of people. I think this can be applied to many areas of knowledge. Yeah. Even in a in a small group, sometimes sharing the right information is difficult. And
Yes.
having everybody on track on the same path is almost impossible. So maybe we have to evolve intellectually a little bit, but it's surprising that the most, taken from the point of view of the regular people in the street like me, that the most analytical minds in the world, people doing your kind of job, cannot realize this or cannot solve this also. No, it's amazing.
You know what a particular problem is with physicists is that they do not consider sociology to be real science.
Okay. Yeah, so only the hard sciences.
Yeah, basically. So if I start talking about sociology, they're like, they want nothing of it.
Okay.
They're not listening. It's like it doesn't affect us. We're too smart to be biased.
Yes, no, you're in a small ivory tower.
Yeah.
Yeah. Don't affected by anything. Okay. Well, let's hope somebody thinks different like you, and you start a new path in this.
Yeah.
Well, why not? Your book is making an impression, I'm sure, maybe in small individuals, not collectively, but who knows? Maybe this is a call of attention to say, okay, we've been doing the same things for 40 years, 50 years, and it's produced almost nothing. So something has to change. It's just the logical conclusion. I understand all the problems that you have said, that people really realizes it, but the fundings depend on this kind of experimentation and LHC and all this. But I can't believe that you are the only one that actually says these problems.
Well, people have spoken about similar problems in other disciplines, like in the life science psychology, this whole issue with the p-value hacking and with the acceptance of bad methods has been around for some while. Yeah, and to some extent, things have been changing a little, in that if you have a concrete problem like the abuse of, say, the p-value, you can just tell people to not do this, like concretely. Do not use the p-value in that particular way, or go and, before you test some hypothesis, go and register your trial where you have to write down the hypothesis. So that's to prevent people from later changing the hypothesis. So these are particular measures that you can take, but it does not address this overarching problem of this whole organization of research being really fucked up. So I think we haven't gotten there, right? And it's about time.
Well, at least you and other people before you say have identified what the problems are. So arguably, there's a way to improve. There's a path to.
Yeah. So yeah, maybe you're right, and I should be more optimistic.
Well, I only can choose to be optimistic because I know I cannot do it, this job. I have to rely on people like you, on real physicists, who to do the right thing. And I don't know. I hope that your book is very well received. It's actually available in English and German, I know. It will be available in Spanish, hopefully by June 2019. I hope it works very well, because it's necessary. It's important that we are not only fed the journalistic vision of science, but also the point of view of a real scientist. So thank you very much for your time and for your research, and I wish that you are granted the funds needed to continue on your track.
Okay, thank you.
Thank you very much.